Okay, good afternoon, everyone. So we're going to continue our discussion of training methods for neural networks. So just to review what we talked about last time, we talked about backpropagation. And the main thing we saw is that in principle, it's not very different from backpropagation in dense networks and MLPs. And one nice thing is that the convolutions that are present in the forward pass also end up being present in the backward pass. And so that means that if you design hardware, GPUs, that are good at doing the forward pass, and they're also good at doing the backward pass, and therefore you can efficiently train and implement these networks. So we talked a little bit about GPUs and why they're important, and we also talked about learning rates and how we can no longer just say that the learning rate just needs to be small enough and we're happy. Now, actually, if the learning rate is too small, the network will get stuck in a suboptimal local minima. So instead, we have to use learning rates that are big enough, but not too big. And then also, it helps to schedule the learning rate. We might start them large and gradually decrease them, or maybe we start them small and then go large and then small again. Or there's even cyclic ones that repeat several times. So there's all sorts of strategies that people have developed that we can use. And then we talked about batch normalization. So this idea is inspired by standardization, which is something that we would do at the input to our network with our raw features. But in batch normalization, you sort of repeat that idea of standardizing the data in every channel and in every layer of the network. So standardization would mean that you make the mean 0 and the variance 1, but actually in batch normalization, you do that as a first step, and then you go one step further and you learn a possibly better mean and variance using a scaling and a shift. And so that's what it does. And then we saw an example from the original paper about how it speeds up training and improves accuracy. And there's a lot of different theories about why this works. Some of them are sort of intuitive. For example, since all channels are normalized the same way, you don't have to worry about some channels having values that are massive and others tiny. Same thing. All the mini batches are normalized the same way. And all the layers are normalized the same way. So that means that layers are decoupled in the sense that without batch norm, maybe what would happen is if one layer was producing outputs that were way too big, and that would somehow overwhelm the next layer, and there would be sort of a coupling where you would make a change in one layer and then that would have effects downstream. But with batch normalization, because you standardize every layer separately, even if one layer outputs very big values, the next layer will immediately standardize them, and so it's not going to be an issue. So all these things help and combine to make training faster, performance better. And there's also theory about how it essentially makes the cost function smoother. So many explanations of why batch norm works. Okay, any questions on batch norm? Okay, so the next thing to talk about is dropout. So what you do in dropout is during training only, you remove, or basically you zero out a large fraction of activations in the network. So in terms of a sketch, maybe this is a neural network where all these dots represent activations and then these arrows represent the processing that's done as you go through those linear stages. And so what you do in dropout is you randomly zero out a number of those outputs, which essentially has the effect of making your network kind of sparse. Only certain activations are left and able to create the output. And by the way, you do this before dense layers only, not convolutional layers. So, so essentially what happens is during training, you see many random instances of this. So it's kind of like you're giving your network a real workout. You're making it really difficult while it's training for it to function. But then, during inference, you don't drop out any nodes and you have the full network. And one way to think about that is that this full network is sort of like a bunch of these guys almost working together in parallel. And so you've trained these individually to work quite well, and then at inference, you combine them all, and it's like an ensemble of simpler networks. The idea of an ensemble, we're going to get into that in the next unit, is where you have many kind of weak predictors that might be trained independently, and then you put them together to make a much stronger predictor. So that is it's one of the interpretations of what's going on with dropout. So that's the main idea. Any questions on that? Okay, so in terms of the details, what you do is, if this is the activation for some layer L, some mini batch I, and some channel M, you multiply that by a random number that takes on one of two values, either 0 or 1 over p, and you keep it on with probability p. Okay, so let's say that p is 0.1. So that means 10% of the time I multiply this, or 90% of the time I multiply this with 0, meaning I take it out of the network. And the remaining time I'm actually going to multiply it by 10, not by 1, but by 10, so that on average, because I'm multiplying it by 10, 1/10 of the time, on average I preserve the value. So the thing you have to choose with dropout is you have to choose this on probability, p. The default in PyTorch is 1/2, but maybe some other values would work better. And you can choose this separately before each layer. So basically that's how this works, and the full network is used during inference or testing. So what you see when you do this is it actually takes longer to train because you're training these weaker networks. Furthermore, the training performance itself is significantly reduced, again, because you're only training with these weaker networks. But then the test performance, when it's used well, goes up. And in fact, the test performance can be much higher than the training performance, because the test performance is with the whole network and the training performance is with these dropped networks there. And then one important thing I want to point out is that this only works if the original network is complex enough so that you can tolerate dropping out nodes. And so what I see a lot in the final projects of previous semesters is that students will sort of optimize their network fully connected like this so that it's working best. And then they try dropout. And they say, oh, dropout is not helping. It's only hurting performance. And that's true because the network was optimized sort of, by that I mean like they tried many different widths and so on. It's really optimized to work without dropping out nodes. Then it's going to work poorly when you do drop out nodes. So you really want to start with a network that is sort of like extra complex, very wide, lots of hidden nodes. And then when you drop out a good fraction, it still works okay. And when you put them all back together, it works really well. So is that making sense, what I'm trying to explain here? Okay. Okay, so that's dropout. Any questions on dropout? Yes.
So the value of P, the probability of the neurons in that layer being active. So during implementation, should we focus on each layer, or just the logic will cover the whole network?
So yeah, so number one, you do this only before dense layers. And so let's say that I have this convolutional neural network like AlexNet, which has 3 dense layers.
Mm-hmm.
So now I could have 3 values of P to choose.
Yeah, that one.
Of course, if I have to choose 3 different numbers,
Mm-hmm.
that is more difficult than choosing one common number that works for all of them. So it's sort of like, these are hyperparameters, so choosing them is a matter of trying different values with cross-validation, which can be very expensive, right? So if I have a single P, then I can maybe make a grid over different values of P,
Mm-hmm.
and that's a one-dimensional grid search.
For each layer.
For each of these 3 layers, yes. The same P for all 3 layers.
Yeah.
One-dimensional search.
Yeah.
If I want to use a different value P for each layer, now I have a 3-dimensional search,
Yeah.
which is a lot more expensive. So maybe I don't have the computational budget to do it. So maybe there exists some triple of different P's that will work better than a fixed P,
Yeah.
but it might be hard to find. So it's sort of a matter of how hard you want to look.
And I wanted to know, like, what is the range that you can use the probability? Like,
Maybe between, I mean, it can be any number, but practically speaking, I don't think you'd want to go lower than 0.1.
and not more than 0.5.
So, but if you did it with 0.9, would it make much of an effect? Is it much different than 1? I don't know. So maybe, roughly speaking, between 0.1 and 0.9, something like that. Okay, good. Any other questions? Okay, so that's dropout. Another thing you can do is data augmentation. And the idea there is that typically the training data sets we work with are smaller than we would like because we would always want to have more data. And so with some data sets, there's ways where you can sort of artificially create more data from the data that you have. And so let's say we're talking about images as an example. Maybe this is one of the images in my data set. So I can create other images that are different than this just by using this. For example, I could zoom into this part of it, and then that gives me this image, which looks different enough that maybe this is treated as actually a different image. Or maybe I could even zoom further, and I can actually make several images out of this. Another thing I could do is I could flip this left to right, and maybe that gives me an image. We have to be careful about flipping up and down with a lot of images because maybe we're working with images where the sky is always on the top and the ground is always on the bottom. If I start flipping those vertically, then that actually might hurt me more than help me because I'm putting in some new degrees of freedom that are actually not present in my data set and not present in my test set. So you have to be careful how you augment. You want to create augmentations that are natural, that sort of mimic the rest of the samples in your data set. And if you do so, you can make a data set like 10 times as big or even more. So it's a very popular technique for image processing. Of course, if you have non-image signals, then you need to think like, okay, what am I allowed to do with my non-image signal? It really depends what kind of a signal it is, what sort of augmentations you could use. Okay, and then the augmentation in PyTorch is done in the data loader. And one interesting thing about that is the data loader is actually implemented on the CPU, not a GPU. So the augmentation stuff you do can actually, if you do too much of it, it can start to overwhelm your CPU. And your GPU might be underutilized and the CPU might be the bottleneck. So you have to be a little bit careful about that. Okay, any questions about augmentation? All right. Another thing we can do is we can improve on our activations. So we talked previously about ReLU, and we know that ReLU was a big advance over the sigmoid because the ReLU prevents the vanishing gradient problem, because for all the positive entries, the gradient is 1. So that's great. Vanishing gradients is largely prevented. But there's a new problem that can occur, that once you train your network and you look at what's coming out of the different activations in your network, you might notice that some subset of them are always outputting 0, no matter what you put in the network. Somehow this is just like some local minima the network has found where it's never using certain nodes, essentially. And so one fix to that is, rather than using a 0 slope here on the left side, you use a very small positive slope like 0.01. And this is called the leaky ReLU. And that small positive slope is just enough to, in most cases, get out of that bad local minima and start to use all those activations and not waste some subset of them. And there's actually a further improvement. The parametric ReLU goes one step further, and it basically allows that slope to be learned. So rather than fixing it at 0.01, it treats it as a learnable parameter. Okay. And this is just a small change that can lead to a decent performance improvement in a lot of networks. Any questions on leaky ReLU? Okay, so now you can go further, and there's been a lot of other activations that have been proposed, but probably the most successful ones are these two, which is the exponential linear unit and the Gaussian error linear unit. So here in orange, we have our basic ReLU. And you can see what the LU does is it keeps this simple line for the positive outputs, but then it gets rid of this sharp corner here and does this smooth thing like this down here. And this shape is specially calculated so that I think if you start with like a 0 mean unit variance Gaussian and you put it through this green shape, then the output is also 0 mean unit variance Gaussian. So it does a nice preservation of certain distributions. And then we have the GeLU here, which you can see is compromising on this slope and compromising on this slope, but giving you sort of an approximation of both that is smooth at the origin. And this one also works really well. So these are all choices for you in practice, and these guys tend to work a bit better than these other things here. Okay, any questions? Okay. All right, so a very interesting thing about neural networks is that some of the things that we learn earlier in the course from classical statistics, like the bias variance trade-off, end up being basically like not quite true anymore. So let me try to explain what happens. So as you probably remember with the bias variance trade-off, so here on the horizontal axis, we have some sort of complexity. So this is for a particular network, which we'll talk about soon, ResNet. And this is the width parameter, which basically means how many channels you're going to use. This particular network usually uses the same number of channels all the way through the network. So that's just a number that you can choose. The more channels you use, the more convolutional kernels you have to learn. So the more learnable parameters in your network. And when navigating that choice, if you think about the classical bias variance trade-off, then you imagine some sort of U-shaped curve like this, where if you go too far to the left, you have too simple of a network and bias is killing you. And if you go too far to the right, you have too complicated of a network, and it starts overfitting to your training data. And that is kind of true in some cases. Here we can see, like, if you did a little experiment where you tested widths between 1 and 8 or something, and you plotted these points, you would notice, okay, there's my bias variance trade-off, and you would be tempted to choose this point here as your network width. And at that point, you would notice that the test error is maybe 0.35, and the training error is a little bit better. And that's maybe what we would expect from what we saw earlier in this course. But what's interesting is that if you go further and you actually try bigger and bigger networks, what you'll see is that test error will actually start to come down again. And if you go big enough, it will actually outperform this point here. And so here we have extremely over-parameterized networks. And when you look at the training error, goes down and basically it hits 0. Okay, so this turns out for most, neural networks, at least big neural networks with big data sets and so on, this is where we want to be operating. We want to be operating here, not here. So this is a little bit counterintuitive if you know the bias variance trade-off, because when you look at this, it looks like you're overfitted, right? It looks like training error is tiny, test error is much bigger. You might say, oh, I should make my network less complex, okay? But that doesn't necessarily follow here. So this thing is called the double descent curve. It was actually kind of discovered by a guy, Misha Belkin, who was at OSU just a few years ago. And it's something that's people are actively studying. It's something that doesn't always manifest, but sometimes it manifests. And so let me give you further explanation. This picture on the right is from the same article. And so the horizontal axis is the same as on the left. We have the ResNet width parameter. But then on this axis, we have the number of training epochs. So the picture on the left is if you train a lot. So it's a slice like this. So basically here, dark blue is small, yellow is high. So if you take a slice like here, you can see it going down and then up and then down again, right? It's dark blue, kind of reddish, and then the darkest blue is over here. So that's this picture. Okay. But that only happens if you train a lot. If instead you only trained for, let's say 100 epochs, you would get this slice, and that would actually look like the classical bias variance trade-off, where it goes down and then it comes back up, and it never gets better as you increase your parameters, right? So this can occur, but it doesn't always occur. It kind of occurs in certain circumstances and important ones, because if you can get here, that's where you want to be. And then if you trained, let's say, for only 10 epochs, you would see that it just looks like things keep getting better as you make your network wider. So it really depends how long you train. And there's various other axes that also exhibit this kind of behavior. Okay, so one of the main points that I want to make here is that so typically you do want to drive your training error to 0. So if that happens, don't immediately say, I'm overfitting. Because it could actually be that is where you want to be with very small, essentially 0 training error. That does not mean, you can see training error is 0 for all of this, but still different parameters give you different test errors. So you still have some design to do, but don't be afraid of having your training error go to 0 and your test error far from 0. That may be where you want to be.
When can we expect this to work?
Yeah, so it's a good question. So there's this link here. If you click on this link, it takes you to a paper that tries to explain several cases of when it can occur. But it's complicated, basically. Like, there's a number of different things that have to come together for this to happen. You can demonstrate it for polynomial regression, for example, but only if you use the right polynomial basis. If you use the standard polynomial basis that we use, it doesn't manifest. But if you use like some Hermite polynomials or something, then it does. So just an example of like how it might or might not happen. And there's ways you can show it even for linear regression, this double descent, but you have to use kind of like a special version of the least squares solution in order to see it manifest. So it's something that if you configure it the right way, you'll see it, but you don't always see it. Yeah. But with neural networks, you tend to see this thing where it works best once your training error is 0. So that's kind of the most important thing. Don't be afraid of that situation. Okay. And yeah, you can click on these links if you want to read more about it. All right, any questions on this? Okay, so let's look at one of the demos for this unit. In this demo, we build our own pretty small CNN, 2 convolutional layers with ReLU and max pooling, followed by 2 dense layers. And we use the CIFAR-10 training data set. And if you remember, that has 32 by 32 color images and 10 different classes, like airplane, and I can't remember all the different classes, but 10 different classes. And on the left here, we have the training accuracy versus number of training epochs. And on the right, validation accuracy versus number of training epochs. And let's look at the baseline method, which is the one I described above. That's the blue curve. So as we're training, you can see that our accuracy is going up to 100%, which we said is not something to be worried about. That is actually often a decent place to be. Of course, we do not expect to be getting 100% accuracy on the validation fold, on the test fold. And so when you look at the blue curve here, you can see it's getting up to like 71%. Okay, so that might be typical, maybe a decent place to start. Now you might say, well, what happens if we add batch norm? So that's the orange curve. So adding batch norm, you can see that training speeds up a bit. At the same number of epochs, we're getting better training accuracy. And validation accuracy is also improved throughout. Overall, at all epochs, seems like we're doing a bit better with batch norm. Now, what if we keep our batch norm and we add dropout? So let's look at the green curves. So now, training accuracy has collapsed. So now it's not getting anywhere near 100%. And you can see it's kind of taking longer. Even after 20 epochs, it looks like we should be going longer. Maybe it can improve further, but it just stopped out of time. But when we look at the validation accuracy, you see a big jump from what we had without dropout. So here, dropout's really helping us significantly, almost 5%. And as one last thing, we said, what if we do data augmentation? And that's the red curve. Data augmentation looks like it's slowing down our training a little bit, maybe because we have more training images to go through, so it just takes longer. And in terms of the validation accuracy, it's helping a little bit. It didn't help very much for this training data set, but maybe, I know for a fact on other data sets it can make a big difference. So it really just sort of depends on the data set. Maybe there's ways we could have done the augmentation that were better for CIFAR-10. Yes?
Does data augmentation really matters even if we have sufficient data set?
So the idea is that in deep learning, you're never content. You always want more data. Generally speaking, if you can get more data, you can do better. So that's the idea behind data augmentation, is that you're never content. You always want more. And yeah, it depends on the data set. Like maybe you have enough, but in other cases, you can see a big gain if you do data augmentation. Okay. All right. Any questions? Okay. So, all right. So let's talk about transfer learning. So transfer learning is motivated by the fact that these state-of-the-art networks have millions, actually maybe hundreds of millions of parameters. And if you want to train them from scratch yourself, it'd be very difficult. You know, generally speaking, this would take weeks, even if you have a lot of hardware to train these things. And so the point is that often you can download the weights for these networks. You let someone else train them. You just download the weights that they trained. But then you keep some of them and you replace some of them. The idea is that when you look at the early layers on those networks, which are the convolutional ones, they're learning things that are very universal, that sort of work for most images. So those ones are okay to leave there. Because let me give you an example. Let's say that we have ImageNet that is trained on 1,000 classes. But now maybe there's something I want to classify that's not in ImageNet. You know, maybe some other kind of images, maybe some particular kind of weed versus a plant, and I don't find that in ImageNet. So what do? Well, we can download one of these networks like AlexNet, and we leave all the convolutional layers the same, and all we change is we retrain the dense layers. And because the dense layers are just a few, this is actually something we can do on our own machines without too much computation. And so you'll do this in the lab for Unit 9. You'll download some images from Flickr, and then you'll take, I can't remember which network you use, but one of the networks, and retrain the dense layers for those Flickr images. And you'll see that it works, and it doesn't take forever. That's one of the applications, is having new data, or maybe you have a new task. Maybe you don't want to do classification. You want to do something different. But you can still use all those convolutional layers, and then the dense layers, maybe you change those, maybe you have a new loss that's not classification, not softmax. Another thing you can use them for is all sorts of other applications. So for example, you guys have probably seen where you take like a photograph and you take like a Picasso painting, and you sort of merge them in a way that your photograph now looks like a Picasso painting, right? So how do you do that? So essentially, you take one of these pre-trained networks, and you push both of those images through the networks, and you look at the feature maps that come out from those convolutional layers. And then you do some clever processing that sort of merges those feature maps. So the high-level details are coming from the photograph. Those would be like the early stages of, the early stages of convolution would have the high-level kind of details, what you want to preserve. But then the later stages would have the textural things like from the Picasso. And so by kind of cleverly merging those different feature maps, you can construct something new. That's just one example of how you can use these convolutional layers. There's many other examples as well. So that's the idea behind transfer learning. Basically, adapting pre-trained networks to new tasks. Okay, any questions on that? Okay, and now, where do you find those networks? Well, the PyTorch TorchVision's models package has many of these pre-trained networks. So a few of them, AlexNet, which we've talked about, and then there's a bunch of others that we're going to talk about next. And part of the reason we're going to talk about these others is that these are listed in chronological order, and we can see by looking at them one after another, we can see how networks changed over time, the tricks that people learned along the way to get us to where we are now. Okay, so let's start with VGG. So we've seen AlexNet. in VGG, so AlexNet had, I think, I'm trying to remember how many layers it had, maybe like 8 layers. So this one has 16 layers, so they grew the number of layers. But in order to keep the complexity down, they used smaller kernels. So if you think about AlexNet, its first layer had an 11 by 11 kernel, right? So each one of those kernels has 11 squared, or 121 pixels to learn, right? Weights to learn, plus the biases. The biases are only, not many biases. And of course, when you have that kernel, you have to learn one copy of it for every input and output channel. So that starts to add up, as we saw. We looked at some of the numbers in AlexNet for some, like maybe the second layer, and it was, I can't remember, but it was like 500,000 weights or something just for that layer alone. So one way to dramatically shrink that is, instead of using an 11 by 11 kernel, which has 121 weights, you could use a 3 by 3 kernel, which has 9 weights, right? So it's a fraction of the weights. But then you could say, well, a 3 by 3 kernel is really much, it's primitive. It's doing a very little convolution, whereas an 11 by 11 is searching over a much larger pattern. Well, the thing about convolution is that if you take 2 3 by 3 layers and you push data through them, you're essentially going through a 5 by 5 layer. And that 5 by 5 convolutional layer would have a kernel, which is itself the convolution of those 2 kernels. So if you go through like 5 of these 3 by 3 layers, you eventually get effectively a kernel that's 11 by 11. But 5 of these 3 by 3s is fewer weights than this. And to make it much more powerful, you actually stick in a nonlinear activation after each of those 5 layers. And at that point, those 5 layers with the smaller kernels and the activations is much more powerful than the single layer with one big kernel and one activation. So this is like the big thing that they learned in going from one of the things, but one of the biggest things they learned in going from AlexNet to VGG. And so in doing this, they're able to go from 15% error rate to 7.5. So basically, they halve the error rate with this trick. More layers, but smaller kernels. Any questions on that idea? Okay. And they had different networks that they trained. They had a 19-layer one, a 16-layer one, 13 and 11, so on. And this won some contests in 2014 in that competition. And this is still a pretty respected network. So if you're looking for a network to download and then use the feature maps from the convolutional layers, this is still one people use today. Note that it does have 3 times the number of parameters in AlexNet, so it does take longer to train. Okay, so that's VGG. Any questions on VGG? Okay, so what we just saw is going from 2012 AlexNet to 2014 VGG 16. Performance got better, but the number of parameters was starting to get very large. So with VGG, we're at 180 million. And so when researchers at that point were thinking forward, they're thinking, okay, well, what they liked is they liked how the networks were getting deeper. They saw that that was really helping things. But they said, we can't just continue growing our parameters because we can't handle that many parameters. So they said, how do we go about designing networks that are deeper but cheaper? Somehow they're getting their depth in an even more effective way. So rather than simply by reducing the size of convolutional kernels, is there something more clever we can do? And one of the things they come up with was these so-called inception modules, and they look like this. So the main idea here is, in parallel, you do convolution with a number of different kernel sizes. And maybe here, 3 by 3, one has max pooling, one does not. And you take the outputs of each of these different parallel convolutional layers and you just stack their channels. And when you do this, the number of channels that you output for the 5 by 5, you don't want that to be many because those channels are expensive to compute. But if you have a 3 by 3 or 1 by 1, those are much cheaper, so you can tolerate having many more channels for those simpler convolutions. So you can see here the number of channels is increasing as you make the kernel size smaller. And then over here, max pooling can also tolerate a lot of channels. So this is the inception module, and this allowed them to go up to 22 layers from 16, but only 5 million parameters. That's a huge reduction, right? From 180 million, 5 million. And this improved the error rate over VGG by a little bit, 6.7%. And it was called Inception because of this meme from the film Inception in 2010 about needing to go deeper. So that's where the name comes from. Another idea is that when you do these inception modules, these bigger kernels can handle spatially larger features than the smaller ones, and so you get sort of the ability to learn things at different scales. So that's another nice feature of these networks. Okay, so that was GoogleNet or Inception v1. Any questions? Yeah.
So are they concatenating the feature maps over there?
Yes. Yeah.
And the feature maps the feature maps will be of different sizes if we use different filter size, right?
No, because if you think about the way convolution works, like if I use the same mode convolution, I'm padding enough, right, so that I always have the same.
Okay, if you use padding, then.
Yeah, we always use some padding. Well, yeah, basically, most people use the same paddings to preserve the feature map size. Yeah, exactly. Mm-hmm. Now, if you do like max pooling, then you actually would be reducing things. I don't know exactly. I would have to read about how they handle that. But okay, good. Any other questions? Okay, so all right. So as we're going through time, then now at 2015, we were seeing that the best networks were getting deeper. But as people tried to go even deeper than 22 layers, what they saw is that there was a new problem that emerged. So vanishing gradients is sort of a problem that when training, so vanishing gradients is sort of a problem we discussed where if you use like a sigmoid activation, then because the slope is very small, when you propagate through many of them, the gradients vanish when you get to the beginning of your network. But there was a new problem called the degradation problem that is basically not solved by things that help vanishing gradients. And so one of the intuitions behind this problem is that if I can somehow design layers such that when I concatenate a layer onto my network, it can somehow act like an identity, meaning it does nothing, then I should not be penalized by adding layers, right? Because I add these layers, but I can always make them do nothing. So they shouldn't hurt me. So the fact that they saw that that was not happening suggests that maybe the issue is that when I'm adding these layers, which is like linear followed by ReLU, that somehow it's impossible for that to act like an identity. So eventually, as I add more and more of these, things just get worse. So the solution they proposed was skip connections. So here is maybe a traditional set of layers, and they proposed to skip around it. And now if you think about this overall layer, if you set those weights to 0, then the data doesn't flow through this way, it only flows around it, and it's exactly an identity. So this is, with this skip connection, it's now easy to make any layer act like an identity if you want it to, but if you don't want it to act like an identity, you can just make these weights sufficiently different from 0, and then it starts to do something interesting. So that was the main idea behind these residual blocks. Super successful idea, and that was what led to what's called the ResNet. And this idea allows super deep networks, like hundreds of layers deep. No problem with the ResNet. And when you look at the performance, they once again have the error rate. Now they're at 3.6%. So this was a huge advance, and still a very popular design. If you just want to train a neural network for something today, ResNet is almost like the go-to thing you do. They have pre-trained versions at different lengths, or you could train them yourself. It's a very successful network. Any questions on the main idea? Okay. So the skip connection it tells us how it works, and it gives us maybe some intuition about how it's preventing layers from harming us if we add too many of them. But it doesn't actually explain what I think is what's really happening in these residual networks. And so there was a very nice paper that proposed a new understanding of them that goes like this. So just as a simple example, let's say that we have a 3-layer network where we have skip connections across each of these blocks. Each of these blocks would be like a linear layer followed by an activation, for example. And so when you look at this, you can see that at every layer, there's sort of two different ways for how the data can flow. And since there's 3 layers concatenated, there's basically 8 different ways the data can flow through this network. It can go through all the skips, or it can go through all those layers, or it can go through some combination. And when you count them up, there's basically 8 of them in total. And here's an expanded, unraveled view of that network when you consider those 8 different ways data can flow through the network. Does that sort of make sense? Okay, so now with only 3 layers, it's not really too clear what's happening here. But what's interesting is that as you grow the number of layers to like large numbers, like 100 layers, you start to see some patterns emerge in terms of the number of different paths that have different depths. So like this path would have a depth of 2, this path has a depth of 1, this path has a depth of 3. It sort of makes sense. You can imagine that no matter how long this is, there's only one path with a depth of 0, right? And there's only one path with a depth of L. But there's many different ways that you can make a depth of 2, which is in the middle. And so what happens is when you have very large numbers of layers and you look at a distribution across the number of paths, across the number of depths, you see that most of the paths, almost all of them, have a depth of about L over 2 in length. And when you look at that subset of really, those are really, basically it's saying that like paths with depths less different from L over 2, there's so few of them relative to these that they don't really count. And then further, when you look at those, and maybe the ones a little bit above and below L over 2, you notice that the longer paths, they contribute much less gradient because there's more stages of ReLU to go through. And so, for example, in a 110-layer network, paths with length between 10 and 34 are really the only ones that are contributing to the output meaningfully. And so Another way to say it is, when you have a 110 layer ResNet, you really have a diagram kind of like this, where you have these parallel paths, where each of those have lengths or depths of on the order of 10 to 34. So it's kind of like you have a bunch of networks in parallel, where some of the weights are shared across networks, but it's kind of like, yeah, basically a bunch of networks that are shorter, not crazy deep, working in parallel. So ensembles of shallow networks. And they did all sorts of nice experiments in this paper to prove that this is really what's happening and what's the description of why these things work. Another thing they showed is that in a ResNet, you can like take out a layer, and it doesn't actually affect the network that much because you still have all the other ones and the data flowing around them. And this actually led to an idea that you can use during training, which is similar to dropout, where you basically drop out entire layers randomly while you're training. This is called deep network with stochastic depth. And this speeds up training and reduces overfitting, very similar to how dropout works, but it works with convolutional layers. So so that's basically ResNets. And these are, like I said, super popular, super successful networks. Okay, any questions? Yes.
I'm not understanding like how, is it just turning certain layers off and on? Like how does it decide which path it actually takes when it goes forward? Does that make sense?
So okay, I mean, the network really does just look like this. Okay, but what's interesting is, what I'm saying is there's another way to think about it. Like these are identical. They're just different ways to picture the same thing.
Yeah, but like, I don't know.
But the data flows in parallel, so the data goes through all those, and then these are additions. Okay, so the data flows through in parallel, and whenever it comes to this, it just adds. And so this is identical to this. Now, so like if you look at something like 1 over x to the power L, so that's a polynomial, right? And when you write this out, there's a binomial theorem. You're going to get 1 plus, I think it's like L times x plus blah, 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 blah. And then you're finally going to get plus x to the L is the last one. And when you look at these coefficients, you'll notice that the coefficients in the middle of the polynomial, the ones with raising x to powers of approximately L over 2, have massive coefficient values compared to this. And so that's kind of like saying, the way that manifests is like, the number of depths in each of these is somewhere between 1 and L, but almost all of them, when you actually count, are about L over 2. So that's the idea behind this. And so those are really the ones that matter because, yes, there is like one path with nothing and there's one path with full, but compared to like the number of other paths, those are basically insignificant. They did all sorts of really cool experiments to demonstrate that. Okay, and we're going to come back to ensembles. That's actually going to be the whole topic of the next unit is ensembles in machine learning. Okay, so does that make things, okay, great. All right, any other questions? Okay. All right, then just to kind of finish up, so, we've been looking chronologically over the years, and essentially, like, the networks kept getting deeper, but kept getting more efficient. The performance kept getting better. But eventually, the performance just kept getting closer and closer to, almost perfect. And after the ResNet, there was sort of one more technical advance called the DenseNet that was designed. The DenseNet, the difference between a ResNet and a DenseNet is in a ResNet, there's a skip connection that's only one layer back from every node. Every node just skips one layer back. In a DenseNet, you skip like that, and then this one skips like that. So you kind of skip back in many other ways. And technically, you do this on a blockwise basis. So you have a block of, I don't know, maybe like 10 deep where you skip back every one, and then you have another block and so on. And this did lead to, better performance than the ResNet, but apparently it's pretty memory intensive to train us. So I don't see this used very often these days. But that was sort of maybe the end of people trying to create networks that were better and better and bigger and bigger. After that, attention started focusing to networks that were something that you could implement like on a mobile device that were much more efficient, but hopefully didn't have too much worse performance. And so, for example, this SqueezeNet, AlexNet performance with 50 times fewer parameters, MobileNet, and so on. So there's a whole bunch of other ones that happened after this, but people kind of switched goals. They said it's not about getting tiny error rates, it's more about like making this more practical. And so again, all these networks you can download in PyTorch, and you can download their pre-trained weights. Okay. So next time we'll go through some code that looks inside the pre-trained networks and so on, but that's enough for today. Hope you guys have a great weekend.